So now we're in section 6.4, another application of integration called arc length. Let me just bring up the whiteboard for a moment. So, of course, an arc, and normally we draw them in red. So, you know, this is an arc, right? You have, hold on one moment. I want to make sure all my notation is good. You know, here's an arc. Okay, you have some initial point and an end point. Okay. Say p sub 1, something like that. Beginning point and an end point, and you want to find the length of this arc length. Now, can you find the length of this arc here? Do you know how to find the length of this arc? The arc, of course, is a line segment, but it's still an arc. Are you able to find the length of a line segment? Did you learn how to do that in pre-calculus or maybe algebra? Indeed. How many remember, that's right, Nathan, how many remember the distance formula? The distance formula for a line segment. Like, okay, Leping remembers that, and some of others do too, Sophie and some others. Let me just see here, I always got to get to the, all right, thank you. So, you know, if you have x1, x2, sorry, let me do that better. X1, Y1, X1, man, this is not being drawn well. Hold on, one moment. Okay, so you have x1, y1. Here you have x2, y2. And what's the length? Do you remember the formula? Now this is for the line, for this line segment.
Square root x2 minus x1 square plus y2 minus y1 square.
That's right, Leping. Very good. How many recall that formula from in the old days? Seeing that? Sure, Sean remembers that. Okay, well let me draw another arc here. Let me draw a circle. Okay, and this circle will have, say, radius 2. Can we find, if we start at this point, okay, if we start at this point here, and let's say we go to this point P1, so here's our arc, say. Usually, by the way, arcs, you know, we put, you know, arrows on for direction. I mean, can we find the length of this arc here? That's half of a circle. Could we find the length of the full circle? Yes. All right, Nathan, how would we find the length of this arc here?
Divide the circumference formula.
Good. Circumference is what? 2. What's the circumference of a circle?
Pi d.
2 pi
2
r.
pi r.
2 pi r. Right. So take 2 pi times 2 and divide it by 1/2, and that'll get you that arc length. So you've already seen how to find some lengths of some sort of famous arcs, a line segment, or like, you know, a circle or a half of a circle. But what if we wanted to find the arc length of sort of general arcs? Well, this is where section 6.4 comes in. It's an application of integration. So let's go ahead and talk about this. Here in figure 2, they have here, I want to be a little careful. I mean, they have a circle, and we know how to find the area, or the length of a circle, right? It's the circumference. But if you didn't know that formula, how would you estimate the length? Well, you could use line segments, and like in figure 2 in the first picture there, you could add the lengths of the 4 sides of that box, okay, and that would get you an approximation to the length of the circle. In the second picture, they have a hexagon. You could add up 6 line segments. In the third picture, you have an octagon, okay? How many have heard of octagon in terms of, like, I guess, what is it, boxing, or the octagon ring or whatever? How many have heard of that? Okay, Sean has, okay. You know, and so clearly, if we were to approximate the length of an arc, this idea, this strategy of inscribing line segments or approximating the arc by adding up distances of line segments seems like a valid approach. And we can be very general about it. I mean, here we are. Here's figure 3. Okay, figure 3, where there's an arc, and it goes, it's not an arc that we know about. We've never found the length of an arc like that. It goes from an initial point P sub 0 to an end point P sub n. And they say, well, okay, let's put in line segments all along the arc, and we'll approximate the length of the arc by adding the lengths of those line segments. So it's a good strategy, and clearly, the more line segments we use, we have to make them shorter, but the more line segments we use, and they're all the same distance, by the way, the line segments. The more line segments we use, the better the approximation is going to be. So, but we have to come up with a formula here for arc length. So here's what we're going to do. Let's suppose that a curve C in 2-dimensional space in the xy plane can be described by parametric equations where x equals f of t and y equals g of t. Okay, and t goes from A to B. Now there's a very like for a circle, what would the parametric equations be for a circle? Do you remember from your pre-calculus days? What would x equal? What would y equal? What functions of t would trace out a circle? Well, how about cosine of t and sine of t? That would trace out a circle, and t would go from 0 to 2 pi. Okay, if you put your calculator in parametric mode or at Desmos in parametric mode, you could trace out a circle. All right, and what we're going to do is we're going to do the following. So, okay, here again, here's the picture, figure 3. And if we want to approximate the length of that arc, we would just add up all the distances of each line segment using the distance formulas for the distance formula for a line. But then as we take more and more, as we take smaller and smaller line segments, they'll fit the arc better and better approximate the actual length of the arc. And so the actual length of the arc of actual length of arc C is just the limit as n goes to infinity of the sum of our line segments. But for computational purposes, we need a more convenient way to compute this arc length L. And so what we're going to do is we're going to do the following. And let me just show you here. So I have some things highlighted here. So the length of the ith line segment of a polygon is given by the square root of delta xi plus delta yi squared. Now let's talk about that. Let's talk about that, okay? As a matter of fact, we're going to try to, all these 3 formulas here, we're going to try to talk about. So let me bring up the whiteboard. Okay, let me bring up the whiteboard. And let me draw a line segment here. Okay. Now, one moment. And, well, hold on. Hold that thought.
Professor, you're muted.
Sorry, class. Sorry. So I got thrown out. Thank you, Samuel. I got thrown out of the room for a minute. I guess I hit the wrong button. What I'm doing is I'm doing this again. I've drawn a line segment from one point to another point. Okay, and the first point has coordinates x1, y1. The second point has coordinates x2, y2. Now, what's this distance here? What's this distance here?
x1 minus x2.
I'll tell you what, why don't we do x2 minus x1? Good, LePay. Absolutely. What's this distance here? That's vertical distance. That's right, Jacob. y2 minus y1. And if you don't mind, I'll call y2 minus y1 delta y. How many remember differentials from calculus 1? Okay, good, good. x2 minus x1, I'll call delta x. And so if I want the distance from between these 2 points, okay, that's how we denote distance. This is another way of saying the distance between the points pi and pi minus 1. Well, couldn't I express that just as the square root of delta x squared plus delta y squared? I mean, isn't that just the distance formula? I mean, are we good with this so far? All right. Are there any questions? All right. And if you don't mind, I'll call it delta x sub I and delta y sub I, just because this is my ith line segment here. Ith line segment. We'll note that what I want to do here is it is the Pythagorean theorem. That's right, Renat. That's exactly what it is. And in fact, because x equals f of t and y equals g of t, well, if x, let me do actually, hold on. I'll show you what I'm meaning to do here. X equals f of t, right? So what we're doing is the curve traced out here has parametric equations. X equals, so I haven't drawn a curve, but you know, I could you know, put in a curve here. Here's some curve C, okay? And the curve C has parametric equations. X equals f of t and y equals g of t. Well, if x equals f of t, x prime is equal to f prime of t, right? In other words, dx dt is equal to f prime of t, right? But dx dt, that derivative can be approximated by a rate of these differentials. So delta x divided by delta t is approximately equal to f prime of t. Okay, how many learned that the derivative can be approximated by the ratio of these differentials, of two differentials? In Calc 1. Okay, Sean recalls it. And all right, well now, and you'll see that now look, if delta x over delta t equals f prime of t, or it's approximately f prime of t, that means delta x is approximately, and if you don't mind, I'll use well, yeah, delta x is approximately equal to f prime of t times delta t. And with this result here, we can say that our length of our line segment, which was by Pythagorean theorem equal to the square root of the sum of delta x squared delta y squared, that can be that can then be delta xi, you know, can be replaced with f prime of ti times delta t squared by virtue of this formula here. And delta yi can be replaced by what squared, do you think?
G prime of t.
Yeah, g prime of ti times delta t. So this is actually what they have in the book. Okay, so what I want to do now is go, are there any questions? I mean, I'm going to go to the book now where they have this statement and continue on. I want to show you how the arc length formula, how they derive it. Okay, because it is important. Okay, Jacob's good. Are there any questions? Nathan?
So why is f prime of t only approximately equal to delta x over delta t?
Well, the formal definition of a derivative, I mean, one of the definitions that you might have learned is that, hold on, f prime of t equals the limit as delta t approaches 0 of delta x over delta t in this case. I'm going to recall that, maybe something like, seeing something like that in Calc 1. Okay, Sean has seen it, and Christopher, and somebody else did. Hold on here. That's why, Nathan, because the true derivative is equal to the limit of the ratio. It equals, I mean, dx dt is, it is a rate, and it's you know, rise over run. It's a rate, but it's as delta t goes to 0. In other words, delta x over delta t, think of that as the slope of a secant line. Think of this as the slope of a secant line. And when you let delta t goes to 0, as it approaches 0, the slope of the secant line becomes the slope of the tangent line, which is the derivative f prime of t. That's why we have approximation here. Does that help?
Yeah, that helps. Thank you.
All right, you're welcome. You're welcome. All right, well now we go back to the book, and you know, they what I've highlighted in yellow, you've seen, and now basically we're let me just take a little bit of this. Hold on here. Take a little bit off here. So now the distance from the 2 points can be expressed. The delta t squared can be factored out of the square root as a delta t. And so the distance of the line segment is equal to the square root of the sum of f prime of t squared plus g prime of t squared times delta t. But what are we going to do with that? Well, all right, the length of the arc then is approximately equal to the sum of the lengths of those n line segments that they use that they use for the arc. They draw those n line segments on the arc, and then you add up the lengths of the line segments. But it's an approximation. So what we have to do is, in order to get the exact length of the arc, what do we have to do with n? We have to let n go to, what does n going to have? N goes to infinity. That's right, Maria. And hence you get an integral with respect to t. There you go. And that is how you find the arc length. So what you have to do is, for an arc, you have to find the parameterization of the arc first. And once you have that, you can apply this formula. Absolutely beautiful. And there's a three-dimensional counterpart also for arc length. We're dealing with space curves in two-dimensional space, but if you have to take like Calculus 3, Math 280, you'll deal with space curves in three-dimensional space and finding arc lengths for those curves. So, incidentally, I teach Math 280 in the fall. I have a night class, and there are available seats. So if anybody's interested. But all right, well, let's keep going here. So here then is the arc length formula. So what I want to do is I want to go ahead and look at some examples with you. Okay. I'll look at some examples here. And A and B are your t limits, by the way. Let's go ahead here and let me bring up an example here, and let me give you a moment to copy this example down. Okay, so we want to find the length. We want to find the length of the arc of the curve described by these parametric equations. So the x-coordinate of the curve is defined by x equals t squared. The y, I'm sorry, let me say that again. You're going to have an arc, some arc, and there are coordinates. There are coordinates on the arc, right? Coordinates. So this arc C, there are coordinates on the arc. The coordinates, you know, are x, y coordinates. So as t changes, you get different points, and that traces out the arc. And the arc goes a certain direction as t gets larger. So this says the arc lies between the points 1, 1 and 4, 8. Well, what would the value of t be, t equal, for 1, 1? What would the starting time be for this arc? Good, that's right, Nathan, that's right, Jacob, t equals 1. Because 1 squared and 1 cubed, hold on, let's do this. Yeah, 1 squared, let me do this right. So 1 is like 1 squared, and 1 cubed equals 1. So that means t has to equal 1 to start with. Okay, now what about for the end point, 4, 8? What's t equal to for the end point here?
2.
What would it be? 2, that's right. Because 4 is equal to 2 squared, and 8 is equal to 2 cubed. Okay, so we know our starting and end times. Now what we can do is we can actually graph this curve if we want an idea of what sometimes it's nice to see what the arc looks like, right? So let me go into the graphing calculator for Desmos, and I'll bring it up here because Desmos is popular. Let me see here. Let me bring it up. Okay, so what you do here in Desmos to graph parametric equations is hold on. Wait,
That was a misclick.
I'm sorry?
That was a misclick.
Oh, okay, no problem. No problem. So I'm going to type T. This is what at least I was reading about. Hold on. T. There we go. Parentheses. T. Sorry. T squared comma t cubed. So it's like you're plotting a coordinate. It's just the coordinates given by the two parametric equations. And t goes from 1 to 2. Okay, now what I can do here, let me zoom out a little bit. And, you know, let me see, let me just kind of, there's a lot of wasted real estate here. So I'm just kind of zooming in, zooming out, just to get kind of a nice window. And so there we've graphed this arc. We've graphed this arc. And, you know, it's not a bad idea to graph the arc, because then we can get an idea of maybe what a reasonable answer is for its length. Okay, we might get a reasonable answer in terms of oh, but wait, hold on now. Yeah, notice the arc starts at 1, 1. Notice the arc starts at 1, 1 and goes to 4, 8 as expected. And let me just see one thing here. One moment here, class. One moment, please. Let me see. Oh, okay. Hold on. Give me one moment. All right. So looking at the arc, what do you think a reasonable length is? Just using your eyes, your eyeballs, eyeing it. I mean, so Jacob thinks it's around 7. Okay. I think that's pretty good. How do you think maybe it's 8, somewhere between 7 and 8, maybe between 6 and 8? What do you think? How many are happy with the estimate of 7 as the length? Okay, between 7 and 8. Nathan says Sophie's good, Samuel's good. Okay. All right, so we have kind of an idea of what a sensible answer is. Now, when we compute this length, we're going to get an exact length in simplified radical form. WebAssign's going to want that. Now, sometimes WebAssign will want length in approximate the length as a decimal. But this problem, simplify radical form. But we know as the answer for the length. But we know whatever the exact answer is, it should, if we convert it to a decimal, if we approximate it with a decimal, it should be around 7. In other words, what we're doing here is called reasonableness of the answer. Reasonableness of the answer. Okay, so let's go back. Let's go back here and take a look here at our, hold on here, one moment. Got to get the file back. Okay, so here we go, solution. So what I've just drawn here is a picture on the right. And picture on the right is just the picture that I had in Desmos. And these here are just if we're using like the TI calculator, TI 8384, you would have to go to mode and put your calculator in parametric mode, PAR. And then T would go from 1 to 2, and I use a scale of 0.10. Okay, the T scale of 0.10. And then X, my X min and max is 0 to 10. My Y min and max is 0 to 10 with an X scale, Y scale of 1. Okay, so if you, but at any rate, all right, well, let's go ahead here. So remember, in this problem, X is equal to T squared and Y is equal to T cubed. So dx dt here would equal 2 times t, because the derivative of t squared is 2t. The derivative of y, derivative of t cubed, is 3t squared. And the limits, the t limits go from 1 to 2. Now the question is, how do we integrate this? Okay, it is amazing to me how often how difficult a time students have with this integral over the years. You know, this is a very famous problem, and you know, I see a 4t squared and I see a 9t to the 4th. I see there's a common factor there, right? What's the common factor between 4t squared and 9t to the fourth? What's the common factor? T squared. When you see a common factor, what do you typically do? When you have the sum of two terms with a common factor, what do you do with the common factor? You factor it out. That's right, Jacob. And that's what I'm doing here. I'm going to factor that t squared out. But the square root of t squared, in this case, is t. Now, normally the square root of t squared, the square root of t squared is the absolute value of t, right? But our t limits are both positive, so that means t is a positive t. And we can drop the absolute values. Are there any questions up to this step here? Okay, so what's going to be then a good approach to use here to integrate that, to get that antiderivative? A u substitution. Absolutely, that's right, Sophie, and we'll let u equals 4 plus 9t squared. And so now our integral, the arc length, becomes an integral with respect to u. The 40 comes from, well, 4 plus 9 times 2 squared, because the original limit was t equals 2. And the 13 comes from 4 plus 9 times 1 squared, because the original limit was t equals 1. And now it's just a section 5.5 problem. But please let me know if you have any questions. All right, and are we ready to move to the next page? Okay, good. Good, excellent. Okay, well, let's move to the next page then. So here we are, finding this length. Of course, I'll bring the 1/18 out in front of the integral, and square root of u is u to the 3/2. The antiderivative of u to the 3/2 is 2/3 times u to the 3/2, and we just work it out. Now WebAssign would take this. WebAssign would take this answer here for the length, I'm sure. But if you wanted to put radicals in there, you could rewrite the answer this way.
Will it take it as a decimal?
It will not. It will not take it as a decimal. It needs the exact answer. What will happen is when WebAssign, you'll have problems where it says find the length of this curve. And when it says that, it wants the exact length. But if it says find the length of this curve, approximate to 2 decimal places, then they want you to approximate the integral. Okay. All right, so we get this answer, and if you go into Desmos and compute this answer, okay, you'll see that it's actually the decimal. Hold on here. Yeah, for this length here, it turns out to be 7.63, 7.634 to 3 decimal places. So pretty confident that we did our integration right and that we got the right answer. Pretty confident. Okay. Does anybody have any questions before we move on to the next problem? Okay. Let's do another one. Let's do another one here. Just hold that thought for a minute. Yeah, let me see here. I want to find. Okay, let's look at this problem. Let me give you a moment to copy it down. Okay, so for this problem, we want to find expressions for the length of the arc of the curve y to the 3/2 power equals x, where this curve goes from points 0, 0 to 1, 1. Now, in this problem, well, of course, if y to the 3/2 power equals x, then how would we get y by itself? What do we have to do here to both sides? If we wanted to graph this arc, and in our calculators, for instance, we're used to y equals. In decimals, we're used to y equals. Right, we have to raise, that's right, Jacob, we have to raise both sides to the 2/3 power. And then you'll get y to the first power, because when you raise to a power, you multiply the exponents. 3/2 times 2/3 equals 1. So you're going to get y equals x to the 2/3 power. I mean, I'm just saying we can do that. And so in this problem, when they say find the length of the arc of this curve, well, of course, the curve, let me just, one moment here. I mean, well, I guess what I'm trying to say is, in terms of graphing it, y to the first is y. So y equals x to the 2/3 power. It's the same graph. Okay, so I just did that so maybe you feel just a little more comfortable with it, But what's missing from this problem? Like, what are the other problem? The problem we just did. Yeah, it had a t in it. I mean, clearly the function y to the 3, x equals y to the 3/2. Okay, x equals y to the 3/2 power, or equivalently, y equals x to the 2/3 power. That's a curve. It's an arc in the xy plane. So it is an arc, and it has to have a length, but where's the t? Where's the parameter? Well, what we have to do is we have to come up with the parameterization for this curve, and it's not that hard. Okay? Let me ask you this. What if we, instead of letting t be a parameter, if we were to just work with this, the arc, the way it's written, x equals y to the 3/2 power. If we were to choose a parameter instead of t, could we choose a parameter y or x? Could y or x be a parameter? And if one of those variables could be a parameter, would it be better to have the x as a parameter or the y as a parameter in this case, since x equals y to the 3/2 power? What's a better parameter, x or y? Use your instincts. Use your other instincts. It would be y. I'll tell you why, Nathan. Let me ask you this. What's the independent variable here? If x equals y to the 3/2, if you have, and I appreciate all responses, if x is equal to some function of y, what's the independent variable? X or Y?
Y.
Well, it's really the Y. So I understand what Nathan's saying. You could always rewrite the equation and make X your independent variable. But if I didn't want to do anything with this equation, okay, then X would be a function of Y, and I would intuitively think of Y as my independent variable. I know it's not something that you're used to doing. You're always thinking X is your independent variable. But there's nothing wrong with here thinking of Y as your independent variable and X is your dependent variable. I mean, let's try that. Let's try that. So here's what we're going to do. That's right, Leping. Here's what we're going to do. We're going to let Y be the parameter. There's two methods here. We're going to let Y be the parameter. And we'll note that since the curve goes from 0, 0 to 1, 1, well, all right, Y equals 0 is the starting value of that parameter, if we want Y to be the parameter, and Y equals 1 is the ending value. Now, what you're used to seeing is you're used to seeing you're used to seeing this formula here, and that's when T is the parameter. But now we're letting Y be the parameter. Okay, so instead of this formula, you're going to have this formula. So you still have dx something squared, dy something squared. You still have that, you know, in the formula. But here, y is your parameter. So instead of dt in the bottom, you're going to have dy in the bottom. And instead of integrating with respect to t, you're integrating with respect to y, because y is the parameter. So here is your, I mean, and so this formula collapses then into this formula. So the book gives this formula, okay, and they say that's when y is a parameter. When y is a parameter, the length of your arc is given by this formula. I'm trying to show you why it's true. Is this helpful, this little kind of thing I did here, this going from here to here? Was that helpful for you? Okay, good, Michelle. Good, Sean. Thank you, Michelle. Thank you, Sean. I just don't want you to think of the formula as weird. It's not weird. It's not weird. Now it's not weird, right? Thank you, Samuel. Thank you. Oh, yeah, a question? Yes, question?
Where did the dy over dy come from?
Well, if we look at the formulas side by side, okay, when t is a parameter, this is your formula, and you're integrating with respect to t. When y is your parameter, I mean, just think of if y is your parameter.
Oh, I see.
Yeah,
Okay,
yeah.
never mind. Thank you.
You're welcome. Okay. Are there any other good questions before we move to the next page? Okay. Nope.
Professor,
Yes.
so the first one is when the parameter is t, and then the other one is when the parameter is y. But what about the third and fourth again? What did you say?
So the first one is when the parameter is t. The second formula is when the parameter is y, and you can even have a formula when the parameter is x.
Mm-hmm. And the third,
But
fourth line,
oh, the fourth line.
the third and fourth.
Well, what I did was, okay, so what I did here then is dy over dy. What's dy over dy equal to in the second formula?
1.
Sorry? 1, hence
Okay.
1.
Got it. And then y to the second power is just 1.
Correct.
Mhm.
Correct.
Okay.
Okay. All right. Yes, Marcus, question?
Yeah, so when would I know when to use like t for the parameter or y for the parameter?
Well, I'll tell you, you can always use t as a parameter. That's going to be the second method I show you. This is the first method, but
Oh.
I'll show you that because I kind of feel like Marcus does. I assume, Marcus, you kind of like the t as a parameter, right? Because parametric
Yeah, I
equations-
guess. Kind of got used to it.
Yeah. I'm used to it too, and so I'll show you the second method. All right. Well, then so since dx dy, remember in this curve, x is equal to y to the 3/2 power, and so dx dy would be equal to dy y to the 3/2, which is 3/2 times y to the 1/2, and here is the expression for the arc length for this curve from 0, 0 to 1, 1. Okay. Now the second method is using the t as the parameter, and I'm pretty comfortable now doing it either way. Maybe it's, I don't know, like a baseball player that can hit with his left or right, on the left or right. I don't know. But I do think it is good. I always feel more comfortable with t as the parameter. So let's say I wanted t to be the parameter. Well, I'm going to have to do something. Well, I'm going to let y equal t. I'm going to let my independent variable y equal t, and then the curve x equals y to the 3/2 becomes x equals t to the 3/2. So in other words, the length of this curve, x equals y to the 3/2, from 0, 0 to 1, 1, would be this. Well, I got to be a little careful here. Hold that thought. No, let me not say anything more on that. So the length, if I let y equals t, okay, if I let y equals t, in other words, I'm going to have t as the parameter, then x equals y to the 3/2 becomes x equals t to the 3/2, and now, well, hey, here are my two parametric equations: y equals t and x equals t to the 3/2. There are my two parametric equations. T will go from 0 to 1, and here we go. There's the length. Absolutely amazing. How many like this second method, method 2, for this problem? Okay, Jacob likes it. How many like method 2 over method 1? How many like method 1 over method 2? Okay, that's interesting. Okay, Audra likes it, Tal likes it, Thomas likes it. Okay, very interesting. Josie, usually it's at least equal, half and half. Nathan likes it. Okay. Well, now you might think, well, gee, you know, I have different my arc length formulas are different, right? Because one has using method 1, y is the parameter, and using method 2, t is the parameter. But in fact, the integrals will give you the same answer. They will give you the same answer. And I'll show you that. I'll kind of make that clear on the next page. But are there, and incidentally here, right, I can write this as 9/4 t. Well, Renat, yeah, that's right. I show the second method for consistency, and because I generally like to, I'm always comfortable if t is my parameter. I'm just comfortable with t as my parameter. So I guess, you know, perhaps Sean and I like the first method or the second method more over the first, but it's okay. We can do it either way. Okay, I'll go to the next page if everybody's good. Okay, so note, using method 1, this was the arc length, that integral with respect to y, and using method 2, this was the arc length, that integral with respect to t. But they're going to give the same answer. They're going to give the same answer. So when students see two definite integrals here, they think, oh, the answers have to be different because the variables are different. But aren't they just the same integrals? It's just one has variable y, the other has variable t. Aren't they just the same definite integrals? That's right. Yeah, absolutely. Absolutely. That's right, Sophie. So, you know, okay. Are there any questions on section 6.4? Yeah.
Professor, if try to use method 2, is there a way to set,
I'm sorry, Ping. I'm having a hard time hearing you. There's some background noise.
okay, I can use is that better?
I can still hear.
Is that better?
That's a little better. Talk a little louder. Talk a little louder.
I say if try to use method 2, so is there a way to set y equal t or x equal t?
Yes, you can always do that. Yes, in fact, that's a good point. Using method 2, you would either set x equals t or y equals t. That's correct.
So either way works, right?
Either way works. That's right.
Okay, thank you.
Okay, you're welcome.
What did the
Are there any other good questions?
I didn't hear what Luping asked a minute ago.
Oh, what Leping said was, if you're going to use the second method, where I mean, sometimes in problems T is the parameter to begin with, like in the first example we did. But other problems, like for instance, if you had like say you had y equals x squared, okay, and you wanted to find the arc length of y equals x squared from like 0, 0 to 1, 1. And you wanted to use just the one arc length formula, the first one you learned. Well, you have to set, if you want the parameter to equal t, what would you do? In other words, here's what I'm trying to say. Let me go to the whiteboard. Let me show you here. Okay, so you have y equals x squared, let's say. So we're that example, we're done with that example we just did. Let's say you have y equals x squared that goes from 0, 0 to 1, 1. Now you can graph that. No problem. Okay. But what would the equivalent parametric equations be that would give you this curve? Well, for parametric equations, you need x equals a function of t and y equals a function of t. So what do you think good parametric equations would be here? If we're trying to model this parabola.
X equals the square root of.
Sorry?
I said x equals the square root of y.
Well, we could do that, but what if we didn't want to do that? What if we didn't want to do that? Couldn't we let x equals t and then y equals t squared? And t would go from, what would your t go from?
0 to 1?
0 to 1.
0 to 1. So that's parameterization. Yeah, generally, yeah, that's parameterization. I mean, I want to do the least work possible. I could take the square root as Renaud suggested, but sometimes when you take a square root, you got to worry about plus or minus and all that. I want the least possible. So look, here's one set of parametric equations, right? Okay, and now here's another set of parametric equations. How about x equals x and y equals x squared, where x goes from 0 to 1. Right? Those, if here x is the parameter, here, and here t is the parameter. So I kind of like this because you're used to parametric equations, like if you graph them, you need x equals something and y equals something. Well, here we have x equals something and y equals something. But if x is the parameter, then x just equals itself and y equals x squared. I mean, aren't these going to give us equivalent, isn't this equivalent, these two parameterizations? Sure. Sure. And I believe, Rayan, are you comfortable with that? I'm trying to recall who mentioned about letting x equal square root of y. But are you okay with this? Whoever mentioned that? Maybe it was Renat. I'm trying to recall. Renat. Okay. Good. 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 Okay. Great. Are there any questions? Okay. Let me go ahead and stop the recording.